to my classes on fundamentals of electrical engineering. We were on the 4th module and we were doing signals and systems. The continuous time systems, along with their mode of solution wherein we use Laplace transforms, have been covered in a few sessions, and some of the discrete time systems with the Z transform coming to the aid of solutions were also covered. Now we move on to Fourier. Then we had moved on to Fourier as well. We had covered 2 sessions in Fourier series when the signals are periodic in nature, and in this session again the periodic signals are being covered to see that the power that is inherent in them, even according to Parseval's theorem, is going to be dealt with. So here we have many signals of different with different waveforms being assessed for their RMS value. Okay? We have root mean square. So a particular kind of interpretation is going to be given to all these signals, wherein the root mean square will indicate the area of that each of the periods of the waveforms will cover. Once that is done, that will give us the square value, and then division by the base of the period will give the mean value, and then we can take the square root. So this is the interpretation that's being given for root mean square value. So let's look at some of the problems here. Starting off with the first one, wherein the general nature of RMS or root mean square value of a voltage waveform as given by Vt equal to 3 plus 4 cos 3t is discussed. Okay? So here we are having 2 components, unlike the physical waveforms that will be covered in the subsequent sessions, problems. So we see that there is a DC value. So that can give us a physical value of a constant voltage of 3 volts being remaining there. The next is going to be 4 cos 3t, which has a frequency of repetition as given by 3, where omega is equal to 3 and 4 happens to be the magnitude. So how do you find the RMS value? Is exactly the method that we'll be using for finding the RMS value of waveforms as well. Okay, so that's the reason why Fourier series and RMS values are coming together in this session. Why? Because only for periodic signals you have power associated with them, and RMS is normally associated with the heat or the power that a waveform can produce. And hence they have what may be called as infinite energy. Okay, so infinite energy means finite powers as per Parseval's theorem, and so we are fine with the periodic signals here. So in this case, we see that it's a very easy way of dealing with such problems. You take the RMS value of each individual component. Okay, you square them and then you add them together and then take the mean value. Okay, and then you take the square root, which gives you what is called as the root mean square value of the combination. So we have 3 square. We also have 4 by root 2, which happens to be the RMS value of the sinusoid. So we have then square them together. Square each one of them, add them together, and then you take the square root. So you get root 17 as the value, and root 17 is the first option, or option A, and we said go for that. Okay. So moving on to the next problem, which is a triangular waveform, but then though the period happens to be t, as is obvious in the diagram, it can be seen that the waveform exists only from 0 to t by 2. So what do you do here? So as was mentioned earlier, the area is the area of the squared waveform is what we are going to how we are going to go about doing this problem. So when you square the components, we realize that the linear portion becomes a parabola, because if y is equal to x is explaining the linear portion. Then we see that the squared value is going to be parabola. Okay, so we have here x squared. So in this sense, so how do you find the area of a parabolic figure, or what can be considered as a cone? Okay, so we take 1/3 the multiple of the base and the altitude. Okay, so this is the way that we are going to do this particular problem. Okay, so what we have here, t by 2 is the base, the height is going to be, even after square, it's going to be 1. So it's going to be t by 2 into 1. 1/3 of it is t by 6. Okay, so divide by this. So now the entire area of the waveform after squaring it, okay, is available with us, but of course for a particular period. Okay, so what do? So divide by the period. What's the period? T. Okay, so t by 6 by t, then take the square root. I hope the way in which we progress with respect to root, mean, square, where we first square, okay, and then we take the mean value and then we take the root is very clear to you. So what's the answer? Root of t by 6 by t is the same as equal to root of 1 by 6. Okay, so again A happens to be the correct option in this case as well. So let's move to a third problem. Here we are having a slightly complex or slightly different kind of waveform. What do we have there? We have a triangle as also a square. Okay, so we know in both respects how we go about doing the problem, because we have the area concept here, of course, after squaring the magnitudes. So in the first case, we are going to end up with a conic kind of figure. So what do we have there? We have the height of it as a square and the base of it as equal to t by 2. Okay, so as before, we see that that's only part of the waveform. The other part is going to be again a square wave, a rectangular kind of waveform with amplitude equal to a. So when you square it, it becomes a bigger square of a square as the amplitude, so long as a is bigger than 1, okay, larger than 1. Okay, so now what do we have? So now there are two components. You have to add them. The areas need to be added, and the total period of the waveform, as can be seen, is equal to t. Okay, so the steps I would relate in the next problem. Okay, so divide by t and then take the square root. Okay, so this is how we go about doing it. So let's read the problem. The RMS value of the periodic waveform ET shown in figure. Okay, ET could be referring to the voltage waveform. So what do we have there? We have yes. Let's start with the triangle, which is now converted into a parabolic kind of line for the linear portion. Okay, so what do we have there? We have a square. That's the total height multiplied by t by 2. Okay, and then 1 by 3 or a square into t by 6. Okay, so I suppose that is remembered from the first problem. Okay, so that's only one part of it. The second part is going to be a square to t by 2. That's very clear. Okay, and the whole, when you sum them together, divide by the whole period, which is equal to t. Okay, and then take the square root. So now it becomes a pure arithmetic kind of situation. So what do we have there? We see that it's going to be equal to a can be taken out, and then of course t gets cancelled. So what remains in the bracket happens to be 1 by 6 plus 1 by 2. Okay, so that's equal to 1 by 6 plus 1 by 2 is equal to 2 by 3. Okay, so that's, and so the square root of that is also coming into the picture. Okay, so again we have now this time we are having B as the correct option from amongst all the answers given. Okay, so in this case, in problems like this, it's better to do the problem and then look at the answers, because you can single it out immediately. Okay, so let's move to the fourth problem. What do we have there? What is the RMS value of a voltage waveform shown in the figure? So what's the waveform like? It's like a rectangular kind of waveform. Okay, so now we need to find out, as was mentioned earlier, the first thing to do in such problems is to find out the period. Okay, so though we missed on talking about such a situation in the earlier situation, in the earlier problems, this problem is absolutely relevant for such an analysis. Okay, so what do we have there? We start from 0. Then the first part of the waveform gets completed by pi by 3, and then you are having the negative waveform. Okay, and then we start the half of the positive waveform only at pi. Okay, so we see that a complete waveform. Okay, so it starts from 0, goes up to 100 volt, and then it goes and it remains there till pi by 3, and then it goes to minus 100 voltage. Okay, and then it remains there for another pi by 3, and then it goes to again 100 volts, and then you have another pi by 3 where 100 remains constant. Okay, and then you have the repetition of whatever has happened so far. Okay, so what do we see here? First, okay, so period is clear. Period can be equal to pi. Okay, if you want, you can even say that if you want to look at 2 periods, then you have 2 pi there. Okay, so even pi is sufficient. Okay, so once that is done, now you look at the square values. Okay, so what is the area? Okay, so to find the area of the rectangle, we see that you have 100 square for the positive waveform, you also have 100 square for the negative waveform. So in total, it's a block of 100 square. Okay, so 100 square a block. Okay, multiplied by pi or 2 pi, divided by pi or 2 pi. Okay, to get the base. The area is given by multiplication by pi or 2 pi, and division by pi or 2 pi talks about the period or the base, division by base. Okay, and then you take the square root. Okay, so square root of 100 square is the same as equal to 100, and so the answer from amongst the given options is D, and we go for that. Okay, so moving to the fifth problem. Here again we are having a different kind of problem, but then we'll have to, as was mentioned earlier, we go for the period first. Okay, so let's read the problem and then go for the period. Okay, so what do we have here? We have a not a distributed kind of rectangles and squares coming into the picture. Okay, the mean square value, it's not the root mean square, but mean square value of the given periodic form FT is asked. Okay, so only the mean square is required. Okay, so the root part alone needs to be avoided. Okay, so let's go for the period first. Okay, so what do we have there? You can start from minus 1.3. Okay, you end up at 0 there. So that distance is that distance is 1.3, and then you go for 0.7. So that's 2. Okay, and then you see that then you have another 2, so 2.7. Okay, so then the whole thing starts off again in the same manner. Okay, so you can go from any point to another point. I have started from minus 1.3. I noticed that there is a 0 voltage or 0 value at the beginning, and this extends for one time period of 1, and then suddenly the waveform rises to a value equal to 4. Okay, and this remains there till 0.7, and that extends up to 0.3 plus 0.7, again a period of time equal to 1. 0.3 on one side, 0.7 on the other side, and then you have again the FT going to a negative value of minus 2. Okay, at t equal to 0.7, and this value remains until we reach 2.7, or from 0.7 to 2.7, the time is equal to 2. Okay, and then the whole thing repeats. Okay, so this is the first observation that we need to make. Okay, when do we start? From where do we start, and where do we end for getting the repetitive nature of the waveform? Okay, so we see that now we are having 1 for 0, 1 second or 1 time unit for the first part of it, where the voltage is 0. Then when the voltage is, or the waveform value is equal to 4, we have another 1 time unit, and then we are having 2 time units for the negative value. So in total we are having 2 plus 1 plus 1, or time period is equal to 4 time units. I suppose this is clear. This is the first point that we have to make clear. Okay? And now we go for the area portion. Okay, so to get the area, we see that 4 needs to be squared, and we have 16 there, and minus 2 needs to be squared, so you have plus 4 there. Okay, so that is okay. So now so 4 for the 16 extends for a time unit equal to 1, so 16 into 1, so the area is with us with the squared value. Okay, so that's only one portion. When we are having 0 voltage, we have nothing, and then we are having minus 2 as the value of the waveform, so that is squared is 4, and that extends for a time unit equal to 2, so 4 into 2, 8. Very simple. So okay, 16 plus 8, that gives us the total area. Okay, divided by the base. Base is of course the same as 4, that gives you 6. Okay, and if you want to take the square root, that's the RMS value. If you don't want to take the square root, you have the mean square value, and so from amongst the answers we pick C. Okay, so moving on to the sixth problem. Again, we are going back to the triangular cum rectangular waveform that we had, and the period is obviously T. Okay, and next we go for the first portion, wherein we are having minus 6 as the amplitude. Okay, and T by 2 as the base. Okay, so RMS value of the periodic waveform given in figure is asked, and the current, and it's a current waveform. So what do? We have identified the period. Next is the squared value. So 36 is going to be the amplitude for the triangular waveform. 36 is going to be the amplitude also for the rectangular waveform. What is the area here for the triangular waveform? 1/3 needs to be remembered, and T by 2 needs to be remembered, as also 36 needs to be remembered. So 6 square, or 36 into T by 2 into 1/3, or 6 square into T by 6 is the area of the partial waveform. Okay, for the rectangular portion, it's even clearer. 36 into 6 square into t by 2, because t by 2 is the period for the first portion. In that case, for the complete period, you can see that it's going to be the rest is going to be, that is the rectangular portion will extend for t by 2. So, okay, 6 square into t by 6 plus 6 square into t by 2 is giving you the total area divided by the base, which is equal to t, that takes the square root. Okay, so in this case, some kind of arithmetic manipulation is has to be done appropriately, such that you arrive at one of the answers. Okay, so don't cancel too many things except for t. So you get the root as equal to you get the answer as equal to root 24. And now you look amongst the answers to see which is the best option. Otherwise, you might be a little confused. So you take out 4 from there. So that gives you a square of which the square root is 2. So 2 root 6. Okay, so this is a better way of doing this particular problem rather than. Or else you can, okay, if you're very quick with figures, you can do it in any manner whatsoever. Okay, so now let's move to a two different kinds of problems. Here we are talking about signal energy. Okay, so that's also the same. In this case, the goodness is that that you also have you don't have to divide by t. Okay, because division by t is giving you the root mean square value or the power content, but in this case you have the entire signal energy, which is, if you remember the Parseval's theorem, it's going to be x square. Okay, so only x square needs to be taken into consideration. Okay, so area has to be taken, but not the base, no division by base. Okay, so what do we have here? We have we have given a waveform in a manner in which it is okay. I'll speak a little more about it later on. Okay, so it is given in a particular in a mathematical format. Okay, so what does it say? The signal energy of the continuous time signal. Okay, so I have drawn it. No drawing was given. Okay, so xt is equal to t minus 1 ut minus 1 minus t minus 2 ut minus 2. That's the second part of the waveform. Minus t minus 3 ut minus 3 plus t minus 4 ut minus 4 is. Okay, so obviously it's a limited kind of waveform. It's not a periodic waveform. So it will have finite energy. So it will be an energy signal. It will not be a power signal. Okay, so actually Parseval's theorem is now discussed in both the kinds of problems. Here we are doing energy. Earlier we are doing the power when we are talking about the root mean square values. Okay, so now. So how do you look at such problems? Okay, of course it's best to draw them. As I said earlier, you can use the area concept much in a easier manner than doing it in any other manner. Okay, so if you are going to draw it, then you should understand what's meant by ut minus 1, ut minus 2, ut minus 4, etc. Okay, so what does it mean? They mean that these ut minus 1, ut minus 2, etc. are talking about the point of start of the waveform associated with the coefficients. Okay, so we start off with t minus 1, ut minus 1. What does it mean? It means just that it starts at t equal to 1. Okay, so at 1 we start off, and t minus 1 tells us that it's having a slope equal to 1. Okay, so we have the signal starting at 1, and it is going on with a slope equal to 1. Okay, but at the t minus 2, what happens is that you're going to have a minus slope. Okay, so minus t minus 2. So if you have already absorbed the fact that ut minus 1, ut minus 2, etc. are indicating the point of starting of that particular part of the waveform, then you can do away with the t minus 1, t minus 2, etc., which come as coefficients. Okay, because it is just telling us in the correct manner. If found other and it's not given in that manner, you can convert it to this format and then continue with the shaping of the waveform. Okay, so we have t minus 1 is simply read as a slope, okay, as a ramp with a slope equal to 1. So we start off with the slope, and then we see minus t minus 2 at ut minus 2. So we stop at t equal to 2 because the next waveform is going to start off. Okay, and what does it say? It says that you are having a negative slope. Okay, and the slope is equal, or in other words, the two slopes cancel. So you are having a leveling off of the signal. Okay, and it continues in this manner until you reach t minus 3. And what happens at at t equal to 3, you see that again you are having another slope, but of course it is negative. So the waveform starts to drop. Okay, so once it starts to drop, it continues in this manner until we reach t equal to 4. Okay, at t equal to 4, we see that a positive slope has now come about. Okay, so we have the negative slope gets cancelled, so we again have a waveform, and so we now have a finite signal. Okay, if you have a finite signal or a limited signal, then you're going to have what is called as a finite energy for it. And what is energy? You just take the areas. Okay, so what are the central portion will have an area equal to it will have an area equal to so the magnitude is equal to 1 in all cases. So we have 1 into 1. So that's 1. And in the other two cases, we are having 1 by 3. I hope it's remembered. And then you are having 2, and then you are having 1 into 1 into 1 by 3. Okay, plus 1 into 1 into 1 by 3 or 2 by 3. Okay, I suppose this is clear. 1 is the time period, 1 is the amplitude, so 1 into 1. Okay, so there are 2 of them, so 2 into 1, 1 into 1. Okay, and then 1 by 3. Okay, because you are supposed to find the area of conical structures. Okay, or the line has become a parabola when you squared it, because we're looking at the area. Okay, just as before. Okay, that's why this problem is also placed along with the others. Okay, so now we have, when you put them together, you don't divide by the base. Okay, unlike in the earlier case, so you have 5 by 3 emerging as the area or the signal energy of the continuous time signal. Okay, so let's move to the 8th problem. Here we have a similar situation, but it looks as though it's a discrete time signal based on the diagram that I have drawn. Okay, it's not given as it is. Okay, so what does it ask? Consider the two continuous time signals defined below. X1 is equal to x1 t is equal to amplitude of t from -1 to -1 to +1. Okay, and it's 0 elsewhere. Okay, so you have a slope. Okay, so I suppose the slope is clear. T is equal to, so from -1 to +1, it's going to have a positive slope. Okay, so we see that, I suppose the diagram tells you that at t equal to 0, it's 0. Okay, on the other sides, they both slope off. Okay, slope off to either sides. Okay, so that's x1t. x2t is 1 minus t. So once we have this diagram, okay, once you have the diagram of amplitude of t from -1 to +1, okay, and at 0 elsewhere, you can just deduct it from 1. Okay, deduct it from 1 means that you are going to have 0 on either sides, and in the center, when it was 0, you are going to have the full L. Okay, so from a shape which is shown beside the question, you see that you have two waveforms. One is x1t and other is x2t. Both are limited signals. Okay, because they exist only between -1 to +1. Okay, so now the question is, these signals are sampled with a sampling period of t is equal to 0.25. Okay, that's why those vertical lines are given, because they are sampled with the sample period of 0.25. So what do we have there? At t equal to 0, you get nothing, but at so for x1t, you see that you are having 4 samples. Okay, at t equal to 0, at t equal to 0.25, at t equal to 0.5, 0.75, and 1. Okay, on either sides. Okay, both for positive t as also for negative t. Okay, similarly for x2t, you are having 1 in the center, then 0.75 on either sides, the amplitudes. Okay, and then again 0.5 and 0.25 and 0 at either ends. Okay. So these signals are sampled with the sampling period of t is equal to 0.25 seconds to obtain the discrete time signal x1n and x2n, okay, respectively. Which one of the following statements is true? Okay, so obviously the x1n has 1 on either sides, okay, and 0.75 on either sides, okay, and 0.5 on either sides, and 0.25 and only one value of 0. On the other hand, for x2n, you will see that there is only one. Though there are 2 0 signals, there is only one signal with amplitude equal to 1. Okay, the others match. Okay, you have 2.75, 2.5, and 0.25. Okay, the energy x1n is greater than the energy of x2n. Of course, okay, when you are squaring them, you get 2 1s. 1 square. Okay, so for x2n, okay, no, so for x1n, for 1 you get for x2n you get only 1 square. Okay, or in other words, so and the others match. Okay, 0 square gives you nothing in both cases. Okay, so it's obvious that x1n with 2 samples of amplitude 1 will have a bigger energy. Okay, have a larger energy. The energy of x1 is n is greater than the energy of x2n. Okay, obviously it's true. Energy of x1n is greater than the energy of yeah, I think that's a mistake. Yeah, so it's repeated. It could be that there's a mistake in the question. Anyway, I'll correct it. x1n nor x2n have equal energies. Neither x1n nor x2n is a finite energy signal. They are all finite energy signals. Why? Because the signals happen to be limited. Okay. I suppose the two important concepts that I tried to convey in this session are very clear to you. One, of course, is that when you are given a waveform, okay, the first and you are supposed to find out the root mean square value or the power in the signal or the mean square value. The first thing that you should do should be to find out, to identify the period of the signal. Once that is done, you can try to square the amplitudes of the waveform. You can see what you get. You can find the area therein. Okay, so if the waveform happens to be composite, add them together, or add individual areas, the squared areas together, and then divide by the base, which happens to be the total period. Okay, so in certain areas of the waveform you may have no signal at all. Okay, so once you have that, you can take the square root, okay, to get the root mean square value, or you can get the mean square value. Okay, so whenever you're having a triangular structure, remember that squaring it will give you what is called as a parabola instead of the line. So you can go for 1/3 into the base into altitude, not half into base into altitude as is normally done for triangles. Here we are having a change in the structure. So you go for 1/3 base into altitude. Okay, the squares and the rectangles are very clear to you. Just by multiplying the base by the altitude, the squared altitude, you get them. Okay, so once all that is done, you add them together, divide by the base. Remember, the base happens to be the period. Okay, and then take the square root if required. Okay. The next aspect is, okay, so these are power signals. So they are not limited. They are periodic in nature. They can be periodic in nature. Okay? But on the other hand, if signals are limited, then they have energy. I hope you understand what is meant by limited. Okay, they are within a particular time frame. So then they are energy signals. So you can definitely go for, again, only the area. Okay, so when you're going for the area for continuous time system, it's simply area. For the other, it's going to be the square of the individual samples. Okay, so if there are more samples, then you have more energy associated with this. Obviously, you'll have more energy associated with them. Okay, that's the intuitive part of it, and even it's the intuitive part that I've tried to explain to you while I'm explaining this particular session in Fourier series. It's a part of the Fourier series. It can be considered both as in terms of the continuous time signal as also in discrete time signals. Thank you.